In this video, we'll talk about circularly symmetrical complex random vectors or random variables. Before that, if you deal with a complex valued random vector for general case, let's say z is a random vector which is equal to x, the real part, plus jy. So this is a random vector, this is a random vector. For the distribution of z, what I encourage you to do is to define w is equal to x, y as a random vector. So here the length is, let's say, n. So here the length is n, and then you have another n here. So you have two n random variables. So what I suggest is usually work with the distribution of w instead of distribution of z or joint distribution of x and y. So w means basically this is like, because this w is like x and y concatenated beside each other. So work with distribution of real part and imaginary part separately, like joint distribution. Otherwise, you may be confused. One of the rare cases that that is easier to manipulate is the circular symmetry case, which we will discuss in this video. And this case is prevalent in many applications in communication systems, sonar, like mammography, and so anywhere that you have baseband representation of a narrowband signal. So a complex random vector, usually you consider z equal to x plus jy, so is equivalent of 2n random vector. So its components are written like that, and then so you have to, so this is why we suggest to work with this random vector w and not with z for general case, except the cases that our formulation may become more condensed and simple, and those cases are the case that we are dealing with a normal complex random vector which has a specific properties, and those properties we call them circularly symmetrical. And let's see why. So suppose that the mean of this vector w be mean of w, which has two components, mean of x, mean of y, and transpose, and then you have to put a transpose on this because it's a column. So this w is concatenation of x and y, so mean of these concatenation of mean. And covariance of w, which is written, so it's going to be covariance of x with itself, covariance of y with itself, and covariance of x and y, covariance of y and x. So you get this one. And if they are normally distributed, the joint distribution of entries of w is like that, and you can write it like that. Obviously, this w is like this vector, and so on. And you see here, you have to have the inverse of this big matrix, and here you have to have the determinant of this big matrix as well. Now, if you write this complex random vector in a complex format, the covariance matrix will become a mean of z transpose z Hermitian, or whatever you want. If you do that, z transpose is going to be x transpose plus x plus jy, and then you will have x Hermitian plus jy Hermitian, and if you multiply them together, you will have four terms. The first term is going to be x transpose x, y transpose y times x, and x times y. If you calculate, apply, then you get the covariance of the covariance matrix of z becomes equal to this one. In other words, the covariance matrix of z will become it has two terms, which is equal to, let me write it. So this is real part, and these two are imaginary parts. So it's going to be cxx plus cyy as the real part of cz, and then plus j cxy minus cyx. So the real part of this is going to be sum of these two guys, and imaginary part is, so in other words, you add these diagonal part in order to get the real part of CZZ, and then you subtract these, the anti-diagonal, to get the imaginary part of Z. So the trick is that if I have CW, I can calculate CZZ. But if I know CZZ, I wonder if I could calculate CWW. Because if you have CZZ, the real part is going to be sum of these two terms, and the imaginary part will be subtraction of these two terms. Okay, so from the complex covariance matrix, you may not necessarily be able to calculate CWW. And this is why there is less information in the complex form than in this distribution. So it is not advisable to use the joint distribution like in a complex form. It's better to work with this one. There is only one exception that is interesting, and the exception is that if CXX is exactly equal to CYY, now if you have the real part of CZZ, just you divide by 2, you get CXX and CYY. We also need that CXY to be equal to minus CYX. In that case, the imaginary part also, if you are divided by 2, you get that. In that case, you can, this information in CZZ is identical with, so these two condition is called circular symmetry condition. This is compacted in a theorem, we call it Goodman's theorem. It says that if you have a random vector like that, and then if you have these properties, CXX and CYY are equal, and CY, XY, and Y, so then we say that they have circular symmetry in second order. Of course, and then in that case, if they are jointly normal, all of them, then I can write this function, okay, this distribution, and I claim that this is going to be exactly equal to FW of W. Okay. So so remember that FW of W was 1 over a square root of, here we don't need to have, we shall not put pi here, this is wrong. So we want to show that the distribution of the random variables can be written in this form. So the distribution that we have written, we have had before, can be written in terms of complex valued. So so if you multiply, this is a complex valued numbers, and this is the mean could be complex vector. This is a covariance matrix which has complex entries. Of course, all its eigenvalues are non-negative. It has all the properties of covariance matrix. But at the end of the day, when you calculate this one, this will become non-negative real number. E to the power of minus that will become e to the power minus a number, and this is determinant. So and this is exactly equal to the distribution that you write the real part and imaginary part separately. So so this distribution, this expression, is a condensed format of writing the distribution for real part, imaginary part separately. So real part, imaginary part, I denote it by these W. So this is nothing more than this one. And if you write that, so remember that in when you write for the real part and imaginary part in this distribution, which is normal, you have a factor of 2, you have a square root here, and then here you have a dimension of this vector is 2n, dimension of this matrix, which should be inverted, is 2n by 2n, and so on. But here in the complex format, the dimension here is n. This vector is dimension n. Here you don't need to have a square root. You don't need to have a factor of 2. So there are some differences, and the big ones is this square root 2 and the dimension of these guys. CWW is a much bigger matrix. CZZ is half the size, yeah, a quarter of the size, because it's n by n. This one is 2n by 2n. And similarly, the characteristic function is more condensed because you can write it in terms of omega, and then here your omega is like can be written as complex. So anyway, characteristic function, we shall not use it, so you can be confused. I don't recommend it. But this expression is often used in lots of journal papers and is correct. So you can easily show that this factor 1 over that is exactly equal to this one, and this expression is exactly equal to this expression. The proof is very easy. So you can use these complex notation for distribution only if you have circular symmetry. Otherwise, the information in CZZ is less than CWW. So if you don't have... There are other distributions that are derived from this formula which are not normal, and for those cases also we can use a complex notation. So this is known as circularly symmetrical normal distribution. And we can only use this expression only if the symmetric conditions are satisfied.